In this tutorial video, I will talk about the Cayley-Hamilton theorem, and we will see an important application of Cayley-Hamilton theorem, which is the Nakayama's lemma. Let me first state the Cayley-Hamilton theorem. Let M be a finitely generated A module. Here all rings are commutative with identity. I, an ideal of A, and phi from M to M be an A module endomorphism. Satisfying the property that the image of this endomorphism is inside I times M. Okay. Now this I times M is the submodule of M whose elements looks like summation, say Ci Mi, where each Ci is inside the ideal I and each Mi is inside the module M. Okay. Then phi satisfies a monic polynomial equation say phi to the power n plus a1 phi to the power n minus 1 up to an equals to 0, where each ai is inside the ideal I. So this is the statement of Cayley-Hamilton theorem. Okay. Now proof. One thing I want to mention that here this constant term an, it is nothing but the this constant times the identity endomorphism. It is not just the constant term. Okay. Okay. Now given that M is finitely generated A module, so we can write M as summation A xi I runs from 1 to n. It means that this xi's generate M as A module. Then also by our hypothesis, we know that the image is inside I times M, right? So phi of xi will be inside this I times M, this submodule. This is true for each I from 1 to n. So we can write this phi of xi as summation aij xj, where j runs from 1 to n, and each aij is inside the ideal I. This is true for all I from 1 to n. Okay. Now we can rewrite this expression as summation j runs from 1 to n delta ij phi minus aij. If we apply it to xj, this will be equals to 0. This is true for each I from 1 to n. Okay. Here this delta ij is the Kronecker delta, means it is equals to 1 when I equals to j, this is equals to 0 when I not equals to j. This is called Kronecker's delta. Kronecker's delta. Okay. Now, okay. Now let consider the matrix, a matrix. Say consider an n cross n matrix whose say ijth entries are bij, bij, okay, where these bij's are nothing but delta ij phi minus aij. It means they are endomorphisms. They are from this, okay, they are a module endomorphisms. And if we means consider this column matrix, say x1 up to xn, we denote it as by simply by x, okay. Then we can rewrite this previous expression, this summation delta ij phi minus aij xj, this is equals to 0. This expression we can rewrite as bx is equals to 0. Here all the multiplications are given by composition of functions. If we we consider here each xi as constant functions from m to m, okay, means each xi, consider xi as the constant function, as the constant function from m to m, means each element goes to xi, okay. And this here this multiplication is given by multiplications are given by composition of two functions, okay. Now we multiply the adjoint of the matrix B in the both sides, adjoint of B times Bx, this is equals to 0. Now from the properties of determinants we can write that we get this is determinant of B times n cross n identity matrix times x equals to 0, okay. Now expanding this determinant of B, we get a monic polynomial, phi to the power n plus a1 phi to the power n minus 1 up to an, okay, where each ai is inside the ideal I, because all these aij's here, these aij's are inside the ideal I. So when we expand the determinant, the coefficients of this determinant of this monic polynomial, this a1, a2 up to an, they are also inside the ideal I. Okay. So from this previous expression we get that phi to the power n plus a1 phi to the power n minus 1 up to an. When we apply this endomorphism to each xi, it will be 0. This is true for each I. Okay. Now these xi's, they generate the module M, right. So this endomorphism turns out to be the 0 endomorphism. So we have phi to the power n plus a1 phi to the power n minus 1 up to an, this is equals to 0. So this is what we wanted to prove, right. So this is the Nakayama's lemma, this is the Cayley-Hamilton theorem. Now we will see an direct corollary, immediate corollary. Okay. Let M be a finitely generated A module okay, finitely generated A module, and let I an ideal of A. Okay. Then there exists a element x say inside M such that x is congruent to 1 mod I. It means that x minus 1, this is inside the ideal I, and x times M, this is equals to 0. Okay. Here the proof, just consider the endomorphism to be the consider phi as the identity endomorphism, okay, and then apply the previous theorem. Then I leave the rest of the details to you to leave the rest of the details to you. Other parts are easy, means easy consequence of this the previous theorem. Okay, just consider this phi to be the identity endomorphism from M to M. Okay. Okay. Now I will state the Nakayama's lemma. Okay, let M be a finitely generated A module I an ideal of A contained in the Jacobson radical, of A. What is a Jacobson radical? This is nothing but the intersection of all prime ideal, all maximal ideals, the intersection of all maximal ideals ideals of A. Okay. Then the Nakayama's lemma states that I times m equals to m. This will imply that m is 0 module. So this is Nakayama's lemma. Now proof. Okay. Now from the immediate corollary of Cayley-Hamilton theorem, we see that there exists an element x inside M such that x is congruent to 1 mod I and x times M is equals to 0, right. Now we need a result on Jacobson radical. I will not prove it, prove the result, but I will state the result. Result on Jacobson radical. Okay. X inside A is in Jacobson radical if and only if, this is if and only if 1 minus xy is a unit in A for all y belongs to A. So an element x inside a ring A is inside the Jacobson radical of A if and only if 1 minus xy is a unit in A for each y inside A. Okay. So for proof, refer Atiyah MacDonald. Atiyah MacDonald, chapter 1. I will use this result. Okay. Now we know that this x is congruent to 1 mod I. So it means that 1 minus x, or say not 1 minus x, or x minus 1, this is inside I. Now from our hypothesis of the hypothesis, this I is contained in the Jacobson radical. Radical of A. So this means that x, which is 1 minus 1 minus x minus 1 times minus 1, this is a unit in A. This follows from this result on Jacobson radical. So this implies that M, which we can write as x inverse xm, x inverse xm, this is equals to 0 because x times m is equals to 0. It follows from the immediate corollary of Cayley-Hamilton theorem. So this is done. Now a corollary of Nakayama's lemma, immediate corollary of Nakayama's lemma. Let M be a finitely generated A module, I an ideal of A contained in the Jacobson radical, of A and N a submodule of M, okay, then N plus I times M equals to M. This implies that N equals to M, okay. For this proof, just consider the quotient module. Consider the quotient module M mod N, okay, and also observe that N plus I times M modulo N, this is equals to I times M mod N. So using this observation, you can means prove this, means you have to use this Nakayama's lemma, okay. I leave the rest of the details to you, okay, leave the rest of the details to you. Now, the most important corollary of Nakayama's lemma. Corollary. Let A M K be a local ring. This is the M is the maximal ideal, the unique maximal ideal, of A, and K is the residue field, means this is A mod M, the residue field. Okay. Let M be a finitely generated A module. Okay. Then M mod small m times capital M, this has a finite dimensional K vector space structure. This is easy to see because this M, yeah. So this maximal ideal M, this annihilates this module M mod MM, this A module M mod MM. So we can think this M mod MM as K vector space, and this is finite dimensional because M is finitely generated A module. This vector space structure of M mod MM, this is induced from the A module structure of M, right. So because M is finitely generated A module, so M mod MM will be also finite dimensional K vector space, okay. Now so this is just observation, but the corollary states something else. Let xi, where I runs from say 1 to R, be elements in M whose images in M mod MM form a basis of the vector space. Then xi generate M as a module. So, this is a statement of the corollary. Okay. Now, proof. Consider the submodule, say n, the submodule of M, the submodule of M generated by the elements xi, I from 1 to n, 1 to r, right. Now, yeah, so n is inside M, this is a submodule. From M to M mod MM, I have a surjective map. This composition map is surjective. Why? Because the elements inside N, this all xi's are inside this submodule M N. So their image will their image will generate this this module M mod MM. From means it is from the hypothesis, this xi generates their images generate the vector space M mod MM. So this composition map will be surjective, right. So from here it follows that n plus mm, this is equals to 0. Sorry, no, this is equals to not 0, this is equals to m. Okay. Now we can apply the immediate corollary of Nakayama's lemma, this previous corollary. Okay. Here this is a local ring, so the maximal ideal, the unique maximal ideal will be the Jacobson radical. So we can apply the Nakayama's lemma or the corollary of Nakayama's lemma, and we get this n is equals to m. So it means that this x's generate M as a module. So we are done. Here these maps are a module homomorphisms, right? A module homomorphisms. Okay. So okay, let's stop here.